Chemical force microscopy, or CFM, is a modification of atomic force microscopy that uses a functionalized tip that chemically interacts with the surface of a sample. Before we talk about CFM, we need to know a little background about AFM. AFM is used to analyze surface topography. A tip on a cantilever moves across a sample's surface, which causes the tip to move up and down as the surface changes. Movement of the tip causes the cantilever to bend. A laser is reflected off the back of the cantilever to a position detector. A feedback loop is then used to adjust the height of the tip as the surface is scanned. Some features that make AFM a good fit for use in analyzing chemical reactions are that it has spatial resolution at the nanoscale, has force sensitivity on the order of piconewtons, can be operated in liquid, and is regularly used already with biological samples. CFM uses an AFM setup with a modified tip. Typically, a silicon nitride tip is plated with gold before a functional group layer is added. The functional group is chosen so that the tip interacts strongly with the chemical composition of interest on the sample. The terminal groups on the tip can form chemical bonds with the sample, which creates a frictional force between the tip and sample. This force is measured and can be used to determine the types of bonds being formed to give a spatial distribution of the sample's chemical makeup. For example, the measured force between a tip and sample can be used by knowing the type of bonds that can form. A sample can be analyzed by knowing the adhesion force, which can be used to map the chemical distribution of the sample. In this case, the adhesion force associated with a hydrophilic bond is the strongest, and the cross interaction is the weakest. One thing that should be noted is that the scanning environment can greatly impact results with CFM. Although ambient air measurements are more relevant for applications, the capillary force causes water vapor to form a meniscus between the tip and sample. This typically has a greater force associated with it, which makes tip-sample bonds more difficult to analyze. Measurements in a vacuum minimizes this issue, but can still be problematic because it is difficult to account for water vapor that has adsorbed to high-energy surfaces. By measuring in liquid, though, the capillary effect is not an issue, and the true tip-sample interaction can be measured. Chemical force microscopy is a relatively new technique, but has great potential, especially for use in biochemistry.